Okay, we'll start today's session. So first I will let me summarize what I the last session I have covered. We are dealing with demodulation of FM waves. We all know that frequency demodulation means basically to recover back our message or original modulating signal from the FM signal. Means whatever transfer characteristics we defined for our frequency modulator, its exact reverse characteristics transfer function we want at the receiver side. In that light, in context to that, hello, so in context to this one, in context of this, we got two methods to discuss. One is a balanced discriminator method that is coming under direct. This we have discussed. Hello. So the slide you can see here, the block diagram has been shown. It consists of two slope circuit blocks having the transfer functions h1 of f and h2 of f. If you look at the transfer functions we have chosen for the both the upper and lower slope circuit blocks have got complementary transfer characteristics. You can see here h1 of f by j, the transfer characteristics drawn for the h1 of f, has got its two gate lobes located symmetrically with respect to the origin, having the bandwidth of Bt. Its complementary version you can see there both the side lobes are have got mirror imaged. So why we need this complementary frequency response is that, so if you look at this total flow of this balanced discriminator, after following the slope circuit, we have envelope detector blocks are there. So these envelope detectors are meant for identifying any kind of sudden amplitude and frequency variations. They are going to identify sudden variations in the amplitude variations in the form of envelope. And whatever the two outputs we are getting because of these two envelopes detectors, we are getting their difference and trying to get the baseband signal. So the total flow you can see here. The first we are applying FM signal, that is S of t, having a complex envelope S hyphen of t. So the frequency response of this S hyphen of t is represented by this H1 of f, having this transfer characteristics. Now let us assume the output of the top slope circuit after passing such kind of FM signal having such kind of complex envelope through the upper slope circuit block, we are getting, let us assume it as S1 hyphen of t. In order to understand what this output will contain, we will have to take the Fourier transform. We will try to understand what it contains in the frequency domain. Let us call its frequency domain version as S1 hyphen of f. So that we are getting with this characteristic. So if you multiply this by j2 pi f and take the inverse Fourier transform, we are getting S1 hyphen of t like this one. So where we are getting S1 hyphen of t in terms of complex envelope S hyphen of t. You need to substitute S hyphen of t here, and if you resolve this one, finally we are getting S1 hyphen of t like this. So S1 hyphen of t we are getting like this one. If we expand this one, we are getting one term containing pi bt AC. Another one is a cosine signal. So it will indicate that S1 of t is going to be an hybrid signal containing both amplitude and frequency variations. So that is will be having a bias term here containing the constant term of pi bt a AC. Means amplitude of the carrier is going to vary, but actually we mean to vary only the frequency in FM. So this is identified as a bias by this envelope detector. We have to nullify it. So that's why we need to have a complementary slope circuit transfer function H2 of M. So this is the main reason, guys, why we are using two exactly opposite transfer characteristics in both upper and lower slope circuits. Hope you understood this one. So later we are going to take the difference of both the envelopes here, and we'll try to balance out the signals to get the baseband signal. So that's why we can see in the center tapped secondary transformer, we got the upper part of the secondary tuned little bit above the carrier frequency by an amount of delta, and lower secondary of the transformer tuned little bit below the carrier frequency. Next it is followed by the R1 C1 filter circuits are there, which are meant to detect the envelope, that is random amplitude variations. So whatever V01 and V02 we are getting, if we are getting them as equal in magnitude, we are getting Fn equal to Fc. And if we are getting one of them is larger than the second one, we are getting positive signal. That will happen if input frequency is larger than carrier frequency. If input frequency is less than the carrier frequency, we are getting the negative output voltage. So this figure you can see it will be indicating the normalized transfer characteristics representation for both H1 and H2 of M. Sorry. So this is indicating the two outputs what we are getting V01 and V02. The difference between the 3dp points of both the outputs V01 and V02 are separated by an amount of 3 dB. So this much difference is required. The dotted line has been shown here to give a reliable output. So this 3 dB difference between these 0.707 points of both V01 and V02 will allow us to get the balanced output. So this already we have discussed thoroughly in the last video. So today we'll start with another method to demodulation of FM wave. So in the phase lock loop, or it is also known as a PLL, it is basically a negative feedback system having three major parts. As you can see in this block diagram, FM wave S of t is applied as input to the multiplier. Means we need another term to multiply with S of t, that is R of t. R of t is going to be an output of VCO, that is voltage controlled oscillator. So here one thing you have to remember, the output of a VCO have got frequency variations according to the amplitude variations at its output input. So that's why it is known as a voltage controlled oscillator. Means we are trying to control the frequency of oscillations in accordance with the amplitude or voltage variations which are applied as input to the VCU. So that is the main job of VCU. Loop filter, you can see it is basically acting like a low pass filter. So all the three, each of these components are connected in the negative feedback loop system, which is going to make your phase locked loop. So all of you listen here carefully what I am discussing. This is very important part. At first, the frequency of a VCO is imprecisely set. Listen here all of you carefully. The frequency of a VCO is imprecisely set at unmodulated carrier frequency. Practically it is there. Okay, that is one thing. Second aspect is output of a VCO has got 90-degree phase shift with respect to unmodulated carrier. These two things are there. Okay. Now let us start the journey. So let us assume before we start the journey, so what kind of FM signal we are applying as input to this PLL, means input to the multiplier first. Let us assume the FM signal S of t is equal to AC sine 2 pi FCT plus pi 1 of t. So where pi 1 of t is the phase expressed in terms of a frequency sensitivity parameter Kf as an integral of message signal. Means we are applying one FM signal with phase pi 1. And let us assume the output of VCU in the similar manner having a different phase pi 2. Okay. So next you can see the whole flow graph we will start here. Now we are applying S of t having this phase pi 1 of t. One thing you remember here, you should compare this how initially we are applying the input in PLL with that of the discriminator method. Here we are applying FM signal S of t having some particular phase pi 1 of t. But there in discriminator we have applied in the beginning FM signal S of t having uh, some amount of amplitude variation there. So if we go back there, what we assumed, complex envelope we assume. Okay. So this is the main point I want you to remember. This is how you have to use the sentences and try to explain the answer in a comparative manner if you want to elaborate the answer. So what is the main point here? In the beginning, we are applying here FM signal having some particular phase pi 1 of t, but there in balanced modulator or balanced discriminator, we are applying FM signal having what? Can anyone tell me? Hope all of you are with me. What is the key point I am telling here? Swapnil? Swapnil is there? Sachin? Amrut? Are you there?
Yes, yes, sir.
What I am discussing?
Demodulation of frequency.
So what I asked, are you able to answer? Rohit Gavibhat?
Sir, in PLL we use phi one of the.
What is there in the discriminator? So this is the key point here. You need to understand what initially we are applying in the case of balanced discriminator.
Sir, demodulator signal.
Sridhar Tadi,
Yes,
Sudarshan
sir.
Kulkarni, Vandana, can anybody respond?
Sir, in balanced signal, we apply a demodulator signal.
What I am telling, in PLL we are applying FM signal as input with particular phase. Like that, in balanced discriminator, same FM signal we are applying but with something. What we are assuming? Here we are assuming some phase pi 1. There what
Frequency,
we are
sir.
assuming? Yes,
Frequency, sir.
frequency what?
Carrier frequency, sir.
Means, are you going to write the answer like this? Question is very much specific. So it will simply tell that you are simply enjoying the classes, turning on the mobile
We
and
add
enjoying
the
something.
carrier frequency, sir.
What?
Sir,
Yes, pardon?
sir, carrier frequency add ಮಾಡ್ತೀವ್ರಿ sir.
No, no, no. Just now I discussed no that one. Here you are assuming a particular phase pi 1 as a part of FM signal. So what similarly, in a similar manner, you may be assuming as we are applying FM signal input in the beginning, in the initial stage itself, to the balanced discriminator. So this one I have told you that FM signal in the balanced discriminator will be having a typical complex envelope is assumed because envelope detector we are using that typical complex envelope we are assuming for the FM signal. So here we are assuming a particular phase pi 1. Similarly, we are assuming particular phase P2, phi 2 for RFT because these two signals we need to multiply using multiplier here. So once you multiply these two signals, you can see here what signals we are multiplying. S of t, that is AC sine 2 pi fct plus pi 1 of t. This should be multiplied with R of t, that what we assume as output of VCU, AB cos 2 pi fct plus pi 2 of t. Now we need to multiply sine and cosine. Simply apply a trigonometric rules, that is sine A sine B equal to half into bracket sine of A plus B minus sine of A minus B. If you apply this one, you work out that one, that I am leaving for you. We are getting two terms here. One is high frequency component that I have shown here. Another one is a low frequency component. So high frequency component we are getting because of summation of pi 1 of t and pi 2 of t, and flow frequency component we are getting because of the difference in their phases pi 1 of t and pi 2 of t. So later such kind of signal having high and low frequency components in the E of t is given as input to the loop filter. Basically the loop filter is going to be the low pass filter. Obviously only low frequency components are allowed. Means what we are getting, the output of loop filter as Km AC AB sine of pi of t. I will call this a difference of pi 1 of t and pi 2 of t as pi of t. Now loop filter operates on this E of t using convolution integral to produce the V of t signal. You can see here V of t signal is there. So if you work out this one, better we are not expecting any steps to solve here. So main thing you have to work out the steps here. That is very simple step. Apply the trigonometric rule. How you are getting high and low frequency components for your E of t. So later, the output of loop filter directly we are writing it as a integral differential equation like this one. So like this we are getting. Okay. So for this one, we are trying to draw our block diagram. That is the extended version of this one. This one is the basic block diagram what we initiated our discussion for our PLL. After getting V of t as integral differential equation, now we are in a position to draw, according to this equation, a higher version of PLL block diagram compared to this one. Compared to this one, we got integral differential equation. Now, based on this, we'll draw the higher version of PLL block diagram. How we draw this one? So D, so you are applying here one input pi 1 of t, and here you are applying pi 2 of t. So how many terms are there? D pi of t by dt, d pi 1 of t by dt is there. Okay. And the third term is minus 2 pi k naught. So if you start with this one, just I am explaining for your convenience to understand. 2 pi k naught is multiplied with integral of sine pi of 2, means it is indicating the convolution integral between pi of 2 and the means it is a convolution integral between these two. So sine of pi of 2 will take the convolution integral of that one multiplied with 2 pi k naught. Okay. So this is one term we are getting here by using this multiplier.
ಏ ಅವಿನಾಶ್ ಸರಿಗೆ ಮೆಸೇಜ್ ಹಾಕು ಸರ್ ಎಲ್ಲದಾರ ಕೇಳ ಸರಿಗೆ.
Hello, am I audible?
ಎಸ್ ಸರ್.
What's the correction here? Okay, we'll continue the session. Okay, is it visible?
ಎಸ್ ಸರ್.
Yes, sir.
Okay, let us continue this one. We stopped at how to draw this block diagram using this integral differential equation. So one thing what we have to conclude here is that I have shown this. Somebody want to join? Let me. Sinusoidal nonlinearity in this model makes it difficult to analyze behavior of PLL. Means non-linearity we are getting in this model because of the presence of this sign factor. So we have to linearize this one to make analysis of PLL easier. That is our next problem. So let us see how this could be done. We can linearize this one by making this pi of t nearly equal to 0. So by experimental analysis, it has been given or mentioned that if you keep the pi of t value less than 0.5 radians, in that case, sin of pi of t will become approximately equal to pi of t. In that case, if you subject this integral differential equation with this condition, that is pi of t less than 0.5 radians, pi of t if we subset this integral differential equation with the condition pi of t less than 0.5 radians, then we can say the loop is said to be in near phase lock. So this is the block diagram we already got. Just I reproduced it here for explanation purpose. And finally, we are getting this integral differential equation. And with this condition, we are making this loop to be locked under the constant phase. There is no any further variation in the non-linearity is not there. So let us continue that discussion. Let us continue that discussion where we left out with integral differential equation. If you take the Fourier transform of this integral differential equation, so you can directly write this equation. We are not expecting any points here. And I am subsetting this Fourier transform of this integral differential equation with this condition. The magnitude of L of f means what it is indicating, the transfer function of the loop filter. If I will assume it to be greater than 1, very much greater than 1, subject to that condition, I am getting this ft of this linear integral differential equation approximately equal to JF by KF KB pi 1 of F. So if we take the inverse Fourier transform, we are getting V of t approximately equal to, hello, 1 by 2 pi kV d pi 1 of t by dt. But pi 1 of t already we know that it is expressed in terms of frequency sensitivity parameter and integration of message signal. If we substitute this one here, we are finally getting expression for V of t, that is output of PLL, containing the ratio of KF by KB times message signal. So L of F here, what I applied the condition here, should be very large for all frequencies. Hence PLL is modeled as a differentiator with its output scaled by 1 by 2 pi kV. So output is scaled down by this amount, 1 by 2 pi kV. So that's why you can see that finally we are getting this multiplying factor as 1 by 2 pi kV. So this is how you have to explain about the indirect method of demodulation of FM. So the another factor we need to discuss today, nonlinear effects in FM. There are two types are there. One is strong, which is a non-linearity, which is intentionally we are introducing in the circuit. Another one is a weak, where non-linearity is inherently, internally available. So in either case, it limits the message signal level in the system that we want to extract or we want to transfer. So here the simple block diagram has been shown here. A memoryless nonlinear device. FM signal you are applying as input, and output we are getting V of t. So for the any nonlinear hello, for any nonlinear system, the relationship between the output and input is given by this equation number 1. That is V of t equal to output A1 S1 of S of t, A2 S square of t, A3 S cube of t, and so on up to plus An S to the power n of t. Now we can see the output V of t is expressed in terms of input S of t, and it is increasing in terms of the higher, and it is increasing in terms of higher power orders. Let us consider the third order, then we'll limit up to A3 S cube of t. Now let us consider what is S of t here. S of t already assumed AC cos pi FCT plus having some phase pi of t, where pi of t is 2 pi kf times integral of message signal. You need to substitute this S of t in each of these terms. A1 S of t means A1 AC cos 2 pi FCT plus pi 1 of t. Similarly, A2 S square of t is there. So in that case, you can replace S square of t by, that is S of t, AC square cos square 2 pi FCT plus pi 1 of t plus AC. Next S cube is there, AC cube cos cube, like this. Now the output consists of a DC component and 3 FM signals with carriers, FC, 2FC and 3FC. So desired FM signal can be extracted by using band pass filter, which is tuned to FC only. Means it is going to select only the first term. So here you can see we are getting only the first term as output of band pass filter, A1 AC, A1 AC cos 2 pi FCT plus pi of t. So it's same as that of the FM effect. That's what demodulation we are expecting. We are getting the same signal as the S of t we apply. means it will indicate that what are the implications or effects. There are nonlinear effects. Amplitude nonlinearities of FM system does not affect the amplitude nonlinearities of FM system does not affect the FM signal.